Ага. Good evening.
По-английски надо говорить?
Да, по-английски. Good evening. Our today's speaker is Maxim Grigoriev, and he will speak about background fields and symmetries in the gauge PDE approach. Yeah. Maxim, you're welcome.
Like this, right? Okay. Okay, hello to everybody. Thanks for giving an opportunity to give a talk here. So it's an old story. Next chapter of the old story about this kind of generalization of concept of PDE, which incorporates gauge symmetries in manifest way, and which allows to treat them differently. But the accent of today's talk is to consider this situation, which is well known in physics, but strictly speaking, under different names, it's also known in math. And the concept is called background fields. What does it mean? It's kind of difficult to give a definition. Well, in fact, the object I'm going to define will be probably a geometrical definition of this concept. Possible, maybe there are other. But the idea is as follows. Suppose we are interested in studying something very simple, like scalar field living on a certain, say, Riemannian space. So we have manifold X equipped with, well, in physics, we would prefer Lorentzian signature, so it's pseudo-Riemannian, but all these issues are irrelevant for the present talk. And the standard answer to do it is to write the following action functional. And it's convenient to keep the dependence of the action functional on this metric, which is usually called background metric, because we think that there is a certain background, certain geometry, or you can phrase it differently, on which there is like additional system defined, additional, in this case, variational partial differential equation. But the dependence on G is kind of parametric. But in fact, you can, when you write action, you don't really see formally a big difference between this metric and the scalar field itself. So what you write the action functional. So I distinguish by bar the different types of arguments. So it's kind of parameter. And then there is a scalar field itself. And this action is usually written like I don't care about constants. Anyway, I will make all possible mistakes with signs and factors. So, it looks like this. So we need to make things manifestly coordinate independent. We need a correct volume form, which comes from the determinant of the metric, and then we have the Lagrange density itself, which is G mu d mu phi. I use this curly phi, d nu phi, say minus m squared phi squared. So you can think of this as an action functional, which depends on two fields, G and phi. But what does it mean that G is background? We are not going to consider Euler Lagrange equations originating from variation with respect to the field G. So this is our metric G mu nu, which is in general function of X. But it is still convenient to keep this G here as an argument. The only thing we do, we vary with respect to phi, and we get the standard Klein-Gordon equation, which is covariant, of course, the Lambertian, something like this, when phi equals 0. This is our equation of motion, which we get by varying with respect to phi. And if you vary with respect to G, what we get is, of course,
We
energy.
do not assume that G is Minkowski metric.
No, generic, invertible. For scalar field, there are no constraints on curvature. You can define it on arbitrary background, but potentially the interest of this structure is, of course, precisely to study curving for certain systems. When you start with something, let's say, flat, and then you try to turn it curved to keep consistency. But this is somewhere in the future. Okay, so this is the equation. If we consider variation with respect to G, we up to a coefficient, we get energy momentum tensor of our scalar field. And of course, we're not going to set it to 0 because it doesn't make much sense. But we already see that there is a certain relation between, and this is a very well-known fact in field theory, that there is a certain relation between background fields, symmetries, and conservation laws, because this is a conservation law. If, for instance, after all, we put our G to a particular, if there are killing tensors. Speaking about symmetries in these examples, we can also easily extract some symmetries of scalar field, which emerge when the background is specific. For instance, if G is Minkowski space, then we have clearly Poincare symmetry. This is a well-known fact. And the convenient way to see it from this perspective is to observe that on purpose I wrote this action in manifestly coordinate-independent way. So there is a symmetry diffeomorphisms. If we consider both G and phi as independent fields, then of course this action is invariant under diffeomorphisms. And the transformation is that delta phi is L psi phi, where L is Lie derivative, and delta G is also L psi G. If you substitute it here, it's just because it's geometrically correct expression. Psi is a vector field parameterizing infinitesimal diffeomorphism. It's clearly invariant, not only under infinitesimal, under generic, but we speak only about infinitesimal. So this action, if we forget about the fact that G is not a genuine field, but we still can consider this functional, we know that it is invariant under diffeomorphisms. But once we set G to a particular value, say we say G equal to G0, for instance, Minkowski space, and consider transformations such that L psi G0 is 0, this becomes a symmetry of this action with G set to a particular value, where G is no longer varied because psi is a killing vector. And for instance, if G0 is Minkowskian metric, then this symmetry is precisely the Poincare symmetry, which must be a symmetry of such a system, and it acts in an obvious way if metric is just a Minkowskian metric. So we kind of see these global symmetries as remnants of gauge symmetries, because this symmetry is a gauge symmetry, because the parameter psi, the vector field parameterizing infinitesimal diffeomorphisms, is a generic function of our space-time coordinates. So this transformation is a gauge transformation. And of course, if we add here, for instance, Einstein Lagrangian, we will get a system consisting of metric and phi, where now they are on the equal footing. It's a big field theoretical system describing interacting system of scalar field and gravity. And then for this system, this symmetry is going to be genuine diffeomorphism. But it is still a gauge symmetry of this action, but of course it's slightly sick, because this action we don't really treat as a fundamental action describing our system. We kind of distinguish these two. But this is very helpful, because we extract symmetries from there, we extract conservation laws, from there. So this is a standard technique. I'm saying that absolutely nothing new. This is a standard technique used at least by physicists. Okay, so where does such system come from? Such system typically, it's not so easy to get this system by gauging global symmetry, but some simpler systems, it's easy to get. For instance, consider another system, which is Dirac field. So what we have here, it is described by Lagrangian, which now depends on our complex four-component spinor. I write things schematically. So let's say we are in 4 dimensions, so that because spinors are sensitive to dimensions, so it's better to be concrete. And here we have psi bar, gamma mu, d mu psi, and suppose that we are in Minkowski space. So now G, we have Minkowski metric G mu nu is equal to eta mu nu, and I'm not going to change it. I'm not going to make, in this example, to make the background curved. But I'm going to do something else. So this system, it describes an electron field, for instance. In physics, it has a clear U1 global symmetry, which is simply given by complex conjugation. So the transformation looks like this. Delta psi is just I infinitesimal generator, I psi. And of course, the conjugate guy, the guy with bar, which is complex conjugate plus some additional metrics. It doesn't matter for us now. What is important that here we get minus I psi bar. Of course, because here, so this is multiplied by I, this is multiplied by minus I, but so you get 1, so this is symmetry. That's fine. And this is a standard U1 symmetry, which is related to the fact that this field, in physics terms, this field is charged with electric charge, and this is the respective global symmetry transformation. So what one can do immediately, one can, of course, extract the respective conserved current. In this case, it is precisely electromagnetic current, which is again up to coefficients, and I don't worry about coefficients. If you apply Noether's theorem to this global symmetry, you get something like psi bar gamma mu psi. So this is charge density current of this field. Because this field is complex, so it is electrically charged, and this is the respective current. And this current is conserved on shell, of course, because equations of motion, if you vary with respect to psi, you get just this. So our equations of motion are gamma mu. This I drop mass term to simplify everything. It's not electron, of course. I need mass term here, but it doesn't change anything. Strictly speaking, if I want to speak about electrons, I need mass. Okay, so let's say is 0. So this is our equations of motion. If I go with d mu on this, I should get that d mu j mu is 0 on shell, right? Of course, in this case, yeah, maybe it's a mistake to introduce mass because then I need to adjust this formula. Anyway, it's completely textbook story, so there is nothing deep here. And once we have this this charge, this conserved current, we can introduce naturally, because we know if there is a conserved current, we can couple it to the field which interacts with this charge, and this is precisely the electromagnetic field. And the Lagrangian which we get now depend on psi and A, where A is electromagnetic field. It's a one form. So we have A mu, which is A mu, which is A mu dx mu. And the Lagrangian looks like this. It's the same one, the one we had. Let's say d for x, psi bar, but here we get gamma mu, and we get d mu plus I a mu psi here. So it's precisely this term with A has the structure of A mu, J mu. And because on shell J mu is conserved, A mu gets gauge symmetry. So delta A mu equal to d mu epsilon, where epsilon is now a generic function of space-time. This becomes a symmetry of this term. Of course, geometrical meaning is clear. We get covariant derivative here. There is a local gauge transformation in this U1 bundle. A is a U1 connection in this line bundle, and this is a gauge transformation of this connection. But again, looking at this formula, it looks exactly the same like this, morally. I mean. So there is a field living on a certain background. In this case, it was metric. Now it is electromagnetic field, and the term in the Lagrangian involving both corresponds to the interaction between our gauge field, which kind of emerged from gauging this global symmetry, because here the parameter of symmetry was a constant, but here parameter of symmetry becomes a generic function of space-time. So this is a result of gauging. That's what vaguely people call gauging, but it's a very vague term. So in some different contexts, people mean different things. Another name for this procedure, which I just showed, is called neutral coupling, because we, by studying conserved currents, we find a coupling of our matter field with gauge fields, which describe interaction between this matter. And indeed, this is a standard term in electrodynamics, which describes interaction of charged particles with electromagnetic field. So this is a classical story. Okay, so now after this small introduction, so I hope it was not completely messy and somewhat useful, at least to motivate why studying, putting some order and some geometry on these issues makes sense. So it was kind of motivational part. I'll try to develop kind of systematic geometrical setup to study this situation, this sort of situations. It's not a completely finished, clear work. Still, there are some issues, but some part is kind of clear, and I'm going to present it. And I start, although my examples, especially because they originate from physics, they are about Lagrangian system, about variational equations. The situation is much simpler if we just consider non-Lagrangian setup to begin with. But non-Lagrangian setup turns out to be rather straightforward on one hand, but on the other hand, it's also essentially known. Well, not literally, but there are not many new ideas I'm going to tell you in this case. In one way or another, people know majority of these things. So, and if we are talking about non-Lagrangian systems, so what we are going to study are partial differential equations with gauge symmetry, where gauge symmetry is taken into account in the structure of the respective objects. Of course, if we have a partial differential equation, in principle, we can describe its gauge symmetry. And We know it in principle, at least, but quite often we need, and in this context in particular, we need some partial differential equations where we only insist on kind of part of gauge symmetry. For instance, we don't want to call all symmetry gauge. This may happen, for instance, if we want to describe, for instance, we want to describe Riemannian geometry. So, and we want to think of it as a field theoretical systems. And we have our field, which is metric, which we just discussed. And we have gauge transformation, which is L psi delta G, delta psi G is L psi G, just the derivative. And suppose we don't impose. If we impose Einstein equations, it's known that these are all symmetries, all gauge symmetries of Einstein equation. But if our metric is unconstrained, then of course it's only part of gauge symmetries. Because if there are no equations, we can shift metric in whatever way we like, and it will preserve the empty equation. So it's only a part of symmetry. So we don't want to really call all possible transformations of G gauge symmetry. We want to keep track only of some of them, which are kind of geometrically meaningful. And this system is an example of PDE with gauge symmetry, where gauge symmetry is prescribed, and where gauge symmetry is not all symmetry of this PDE. And there are plenty of examples like this. They arise naturally in applications. So it's a good idea to think of gauge system as a partial differential equation plus concrete prescription for which gauge symmetries we call gauge, and the rest we don't gauge. And there is a geometrical way to sufficiently flexible way to describe these symmetries, and this way is called gauge PDE. I gave few talks about in this seminar about these objects. So, but I'm afraid I still have to to remind you what it is. What do you think? Shall I? Of course, I need to remind definition, right? Okay, so here we use the language of graded geometry. So graded means z-graded. But quite often it's enough to consider non-negatively graded objects. But in general, of course, and for full-scale theory involves z-graded setup. So what we need? First, we need a notion of Q-manifold, or another name for this is maybe becoming even more popular, DG manifold. So it's a z-graded M equipped with Q vector field, which has degree which has degree 1, and which is homological, which means that if we take a graded commutator of Q with itself, this is of course just Q square, this is 0. This means that functions on this guy form a homological complex, and we can speak about various cohomology groups, like in functions, in forms, in vector field, in tensor field, whatever you like. So what is the next object we need is, well, maybe 2 examples which will be basic. So one is called shifted tangent bundle. So it, as a graded manifold, it's just an algebra of exterior forms on X. So roughly we just call.
So X is classical manifold.
Yes, real manifold. Yeah. So essentially, it's what all we do with differential forms, but we treat dx mu. We call it like new coordinate of degree 1, it appears stupid because, of course, it changes exactly nothing. But then on this, it still makes sense to speak about, for instance, differential forms on this guy. And this notation is needed because once I really get the RAM on this manifold, on this graded manifold, it's not this D. For instance, I have d theta and dx, and it's not, I have independent differentials of these coordinates x and theta. And of course, on T1x, I have the RAM differential, genuine RAM differential of x, which now looks like a vector field on T1, on T1x. And I denote it by dx, not to confuse with the genuine RAM differential, which is also needed. And this is the RAM differential. So the RAM differential will mean really the RAM differential on whatever graded manifold we have in our setup. And another example, which is also very useful in to give further less trivial examples. Example of Q manifold originates from Chevalier-Lindbergh complex of Lie algebra. So would we take, let's G be a Lie algebra. Then we can shift it by 1. So so Lie algebra is a real space. Let's say real Lie algebra is a real space. We can think of this real space as a linear manifold. So we just it's a question of which kind of functions we consider there. But then we shift by 1 the degree of coordinate functions of linear coordinate functions here, and we get graded manifold. Of course, algebra of functions here is just algebra of exterior forms on this space G. So it's finite dimensional, just a Grassmann algebra generated by dual basis of G. So for instance, if in my G I have basis T alpha, so introduce coordinates C alpha corresponding to this basis, and now they have degree, which I denote by Ghost, which has 1. Because if I have coordinates on G, not shifted G, coordinates are going to be real numbers. But now I shift them. And algebra of functions in these coordinates, because they are graded, is just a Grassmann algebra generated by this, by this element C alpha, and it's finite dimensional. It's 2 to the power of dimension of G. And suppose I also have a module, or for instance, I have M is a, I'm not sure it's a good notation, G manifold. So the manifold where my algebra acts by vector fields. And then I can form, I can take my, let's say this M naught M to be a product of G1 with M naught, on which I have a standard difference, because functions on M naught is a module over the algebra. So what I can consider, Chevalier-Lindbergh complex of my Lie algebra with coefficients in functions on M naught. And I can identify cochains of this complex with functions in C with values here. And then I can write my differential as a vector field on M. And I denoted dg. And this is, of course, just C alpha rho of T alpha, where rho of T alpha are vector fields implementing the action of basis generators minus half what it should be like CC alpha DODC alpha, right? This is a standard piece of just trivial coefficients. Okay, this is another example of Q manifold which shows up everywhere. Of course, all this can be phrased differently, but this language turns out to be useful in certain applications. So what is gauge PDE? Gauge PDE is a bundle in this specific bundle in this world of Q manifolds, and for definiteness, so gauge PDE it's a bundle E over T1x. X is a space of independent variables. So Q is a vector field on total space. And the requirement is that it projects to the de Rham differential here by this projection. So it's a projectable vector field. In algebraic terms, it means that we have pi star dx equals to q pi star. This means that projection of q is dx. So this is just, it's for the moment, it's just the name for a Q bundle. So it's a bundle in the category of Q manifolds. But for the moment, we insist that the base space is related to our space of independent variables, to space-time in physics in field theoretical terminology. But of course, the interesting part of gauge PDE is not that it's a Q bundle, it's a definition of what solution is and what gauge transformations are. So solutions are defined as sections such that they compatible with this Q structure. So it means that sigma star Q is dx sigma star. So if this holds, then section sigma is called solution. And gauge transformations are defined like this. So first of all, we need gauge parameters. So y projectable vector field on E. It's a gauge parameter. The degree must be -1 for normal gauge symmetries. There are higher gauge symmetries. And the gauge transformations act on sections. So the action of y, so sigma delta y, infinitesimal variation of section, is defined like this. It's sigma star of qy minus dx y, and here we need sigma star here, where y is a projection of y by assumption y.
Capital Y.
Yes, so pi star of capital Y is small y. So often we do not write this part, it's not so important, but sometimes it is useful because we don't want only vertical symmetries. It's useful to have generic projectable vector fields, but then in order for this transformation to change section into section, not to add the diffeomorphisms of the base space, you need to subtract this piece, but for simplicity you can think that it is vertical. Then of course it is projectable, but
so y is projectable
and q is also projectable.
Only q by definition.
Yeah, so these are gauge transformations, these are solutions, and it's not difficult to check that gauge transformations take solutions to solutions. Of course, everything is infinitesimal. So in general, we are talking about infinitesimal geometry, let's say from geometrical perspective. And it's in a similar way, one can define gauge for gauge symmetries by, so what is gauge for gauge symmetry? It's a transformation of parameter, of a gauge parameter, such that it results in a trivial symmetry. In this case, of course, it is clear that you just need to say that delta y is q with, okay, y of next, let's say y1. And now this guy should also be projectable, and of course, the ghost of y1 is now -2.
What is y1?
It's a parameter for parameter. It's it's a transformation of gauge parameter such that it doesn't affect the gauge transformation induced by this parameter. So it's like the kernel of this operator which determines gauge symmetry. For instance, well, it's not the standard example of reducible theory is when you have a two form, for instance, B. So, and you say that your gauge transformation is delta B is deram on one form epsilon parameter, but epsilon you can add a lot. Still, there is a big kernel parameterized by generic function. So you can say that delta epsilon is d of lambda, where lambda is a zero form. Of course, because deram squares to zero, this is called gauge symmetry for gauge symmetry, or sometimes higher gauge symmetry. So this term higher is kind of jeopardized. It's used everywhere in all aspects. So it's, if you want, it's kind of next degree symmetries. They are also interesting in certain situations, and they emerge naturally when you consider theory where you fill the differential forms of degree higher than one. So in Maxwell, you don't get it. If you go to, for instance, two forms, three forms higher, you get this chain of such symmetries.
So Y1 is also a vector field.
Yes, yes, projectable. Yes. Mm-hmm. But degree must be shifted because Q carries degree 1, so to get there. But because Q is nilpotent, clearly this transformation doesn't affect this transformation. So it's called gauge for gauge symmetry. Okay, so the content of this definition is that this geometrical data defines for us certain partial differential equation, which is imposed on section, together with certain gauge symmetries. So hidden in this object, in this geometrical object, there is a gauge theory. So certain PDE together with prescribed gauge transformation and probably this higher order gauge transformation. And what you can prove that you know that a good language to speak about gauge theories is Batalyon-Vygotsky formalism. In this case, it is of course non-Lagrangian version of it. You can't quantize it. You just take care of equations of motion and gauge symmetries, not Lagrangian. And there is a statement saying that if you have gauge PDE, it naturally determines BV system on the associated jet bundle, where the associated jet bundle is, roughly speaking, superjets of this. That's where you find all BV structures. And other way around, it also works, because if you have a local BV system, so jet bundle together with homological vector field, compatible evolutionary vector field homological, which is BV at the level of equations of motion, then you can hook up gauge PDE, which equivalently takes it, reformulates it. And there is a notion of equivalence for such objects, which is generated by what's called equivalent reduction. I'm not sure I'm really going to use it, but let me maybe say so. If I have EQ T1x, this is a notation just to list all structures for if I have such a gauge PDE. Suppose I have a sub-gauge PDE, so which means it's a sub-bundle here, E of sub-bundle of E, so it means that somewhere inside I have another one, which is, let's say, E prime, Q prime, but the base is the same. So there is a sub-bundle, and Q is tangent to the sub-bundle, so I can even erase prime because it's naturally just a restriction, and base is the same. I say that E prime is an equivalent reduction of E if E is a locally trivial Q bundle over E prime with contractible fiber. Of course, when I say that E is a bundle over E prime, it is meant that both are bundles over T1x, and projection is a morphism of these bundles, so it doesn't affect. It does not affect the. So I have E prime. Here is projection. Here is projection to T1x, and this projection, and all these commutes, of course. So it's a bundle of bundles. And it is locally trivial, which means that you can completely separate. You can decompose Q into something emerging up using trivialization from E prime, and the trivial piece, like the RAM, on the contractible fiber. And this guarantees that cogomology is the same, everything is the same, and it's a good notion of equivalence, generates a good notion of equivalence for these objects. And this is what physicists know under the name of elimination of generalized auxiliary fields, because like this fiber coordinates on this contractible fiber, they are going to be such dependent variables for which equations are solved, or they are pure gauge and you can completely gauge fix them, and no topology enters the game because it's contractible, it's just a linear space.
How this bundle of E over E prime corresponds to the embedding of E prime to E.
So there is a projection and embedding. It's very
actually it splits.
Yes. And then so it's enough to say that there is a that one is isomorphic to a locally trivial bundle over another, which admits global section. So there is a real, like locally it's completely decomposed, and there is a contractible fiber over which you can forget about it. But I don't really need this seriously, so I suggest not to spend much time on this. Okay, and now I get to, I need an example, and then I get to already story about background in this language, and maybe it's an appropriate moment to mention that what will come next is based on a recent work with Ivan Dniprov, my PhD student working with me. We put it to archive some weeks ago. So, but maybe before getting to the background, maybe I need a couple of very simple examples of these gauge PDEs so that you get a feeling what it looks like. So let's take usual PDE in invariant terms, which is a bundle over X. X is independent variables plus Cartan distribution. So it's an involutive horizontal distribution on E naught. Then we can consider differential forms on, sorry for using this notation, on E naught. And we can split them into, we can separate horizontal forms, which are like we have horizontal forms, right? Because we have Cartan distribution, we have B grading, we can just consider horizontal forms. And on horizontal forms, there is a horizontal part of the RAM differential. So the RAM differential splits into horizontal piece plus vertical piece. And here we have DH, it rises only the horizontal degree. So DH is a map from P0 of a node to P plus 1. Okay, and so this algebra, we can think of it, we can change language to graded geometry, and we can replace generators of horizontal. These are x coordinates, so dx's, which enter this algebra, which generate horizontal forms. We can replace them with coordinate theta mu. Geometrically, it means that we can see the new bundle E over T1x, which is a pullback. So if I is an embedding of x into T1x, then E is as a zero section, I star of E naught. So very simple. I just, roughly speaking, I just to my initial bundle, I add these fermionic coordinates on the base. So this is my new bundle, and it's naturally bundle over T1x because I took this pullback, and DH, because functions are the same, pullback becomes, I can say that now I identify Q, I take Q to be DH. So what I get this very specific EQ T1x, which I constructed out of a PDE. Okay, and then I can look for solutions. So what are solutions of this guy? And I immediately find that they are, of course, exactly the same. Because what are sections of this bundle? They take, so of course, sigma star of x is x, sigma star of theta is theta, and then suppose I have some fiber coordinates, sigma star of, I don't know, psi a, sigma a of x, and there is no theta dependence here because my fiber coordinates have degree 0. Variables which have degree 1 are only these thetas. So it means that I don't get anything graded. So my sections are parameterized by these functions. So these are one-to-one with sections of my initial bundle. And of course, the condition that they are co-sections becomes just that their solutions become just covariant condition of covariant constancy. Because Q is a connection, or geometrically, one can say that alternative is, of course, if you, yeah, that's a useful point. If you have a Q section, it means that it's a submanifold which projects to the base to which Q is tangent. So it's exactly the same like in theory of connections. So such submanifolds are, of course, covariantly constant sections. So solutions are the same. Solutions are just covariantly constant sections. And there is no gauge symmetry because you can't find gauge parameter. Well, of course, you can find gauge parameter of degree -1, but this is going to be just, it's going to do for you just a reparameterization of your base. And this compensating term is going to kill it. So there is no gauge symmetry. So everything is compatible with the usual story about partial differential equations. Of course, this is not the most general situation, because typically you can assume less, like in Vinogradov's theory, you can assume less. You don't need to require this to be a bundle. In principle, this perhaps can be done. It's more or less clear how it also can be done in this Q language, but it's probably not the most, it's not really related much to what I'm going to talk about. Okay, so this is one example, and another example is, let's take the following. Let's take E to be T1x times just shiftedly algebra with Chevalier-Limberg differential, now of course with trivial coefficients. And this is fiber, this is base, and the projection is canonical. It's possible to make it a non-trivial bundle in general, but let's don't get to these subtleties. So what happens here? So here, let me do coordinates. Here I have again x mu, theta mu, and I have let's say C alpha, just like the notation I introduced. Я на семинаре. Ты чего? Я на семинаре. Нет. Okay, so x theta C alpha. So these are fiber coordinates, these are base coordinates. And let's have a look what solutions are. Solutions are, so we want sigma star dx of C alpha to be, on C alpha we have only Q, so it's just dg acting on sigma star dg C alpha. So what we get is that if we denote by A alpha sigma star of C alpha, but C alpha has degree 1, so A alpha also has degree 1, so it's a one form here.
And X is a G manifold.
Pardon?
X is a G manifold, or just
No, just nothing for the moment.
No action.
No. It will maybe come. So for the moment, maybe no, there are solutions, of course. Yes. So this is definition of solutions, but if we denote by A sigma star of C alpha, what we get is dA plus half AA is 0. So this is zero curvature equation. This is condition for solutions, but of course this structure also contains the gauge transformation, which is delta. Let's take y to be epsilon alpha of x do dc alpha, vertical, sufficiently general. And this is going to give us delta A to be d epsilon plus A epsilon, the standard gauge symmetry. So this is zero curvature equation with a standard gauge symmetry. It's of course a classical example. I don't know where it was written like this, but for sure in this AKZ construction, somehow it was already long ago. I mean, of course, this graded geometrical interpretation of this system. So what is interesting about this guy? It's an example of finite dimensional PDE, which is still reasonable. So it's a certain analog of equations of finite type, but gauge ones. Even though the space of solution is infinite dimensional, because we have plenty of flat connections, but because the quotient space is essentially locally empty, if there is a non-trivial topology, of course we can get a lot. Because the quotient space is empty, it's possible to formulate it as a finite dimensional GPDE. So it's a nice feature. Okay, so let's get to.
I'm sorry, what's the definition of dimensional of GDE?
Well, it's just finite dimensional bundle.
Just finite.
The fiber is your Lie algebra, and the base is your space-time with additional fermionic coordinates. Okay, so now we get to this story about background. So when we, in this definition of GPDE, of course, we could easily replace T1x dx with whatever Q manifold, let's say B gamma. Formally, we can repeat all the story. We can say what are solutions, what are gauge transformation. But of course, this means that you have certain structure there, because to have this structure on X,
is also
any Q manifold serves as a base space. Formally, you extend everything. Of course, it's difficult to say something concrete because this is very general. But of course, the idea why to consider the minimal version of just space-time and the RAM there, the forms, differential forms on space-time plus the RAM, because to have it, you don't assume any geometrical structures on your base space. So you don't, you require nothing. So if there is some geometrical structures which your system describes, they should sit in the total Q structure or in the in the total space, not on the base space. So you don't assume any geometrical structures there. Okay, and so if you want to consider this situation, so in this language, this situation when you have certain fields living on the background of another field, then the idea is, of course, that we can consider this, but we want all of them to be fields. So in fact, we ask all guys to be bundles over T1x. Oh, what am I writing? No. So the story.
Some human fold.
Yeah. So we have we have the following thing. We have EQ fiber bundle over B gamma. It's another Q manifold, which is itself fiber bundle over T1x. Because somewhere deep inside we have space-time. We have our independent variables. Of course, we can get a project. This is also a bundle there. So there are two ways to think of this. I don't know what are right geometrical terminology. It's either like bundle over a bundle over T1x, or it's a bundle in the category of bundles over T1 over T1x. Okay, and here the situation is rather simple because all of them are Q manifolds, and somehow like fiber coordinates here are background fields, and fiber coordinates here considered as a bundle over B are like our dynamical fields, if you want. And what does it mean putting our system to a concrete background? We take a solution of B, so it means that S is a submanifold. It's a section, so submanifold which projects here. It's convenient to define it like this, of B. So let's say here we have P T1x projection and here PB. So of course P of well, okay, it's section. It's enough. I don't want to. It's a section. We consider it as a submanifold here, and it's a solution. It means that gamma is tangent to S. So S is a solution. Solution to B, and then of course what
S is a graph of a section.
Yes, exactly. Thanks. Yes, S is a graph of a section. So what I can do, I can then pull back E to this S. So I can restrict my bundle to S. Of course, it's essentially the same as P as S star. If I think of this as a section, S star of E as a pullback of my bundle. And now I end up with a bundle over T1x, where already like these fields are fixed to concrete values, and they satisfy the equations of this one. Okay, and this construction is by definition is gauge PDE. So of course not very rich and not terribly interesting because it's kind of straightforward, but still it's instructive to look at it a little bit. It's a GPDE over background. So what are kind of properties?
So D is the background, and why GPD, why G?
Because these are all gauge PDEs. There are also
G
gauge
for
symmetries.
gauge.
Gauge, yeah. It's just a short form
Okay.
to say to do some chalk economy. This structure is by definition the GPD over background, where this guy is called background. Once we fixed a solution to the background, we immediately end up with a new GPD, kind of subsystem, which corresponds to these fields living on a particular background. So, for instance, speaking about examples I had, like for instance, this one could describe metric Riemannian geometry, and this one could describe, let's say, scalar field defined over Riemannian geometry. And in this case, for Riemannian geometry, it's not even difficult to do it explicitly. Of course, all these guys are infinite dimensional in this case, and it's sometimes it's preferable to simplify the situation to get something finite dimensional. Okay, so maybe some properties. Suppose that I fixed my solution S, and I consider like new GPD, which is E pulled back to by embedding of S into B. So this GPD in concrete background. Then what about symmetries? There are gauge symmetries which originate from gauge symmetries of this guy. So suppose there is a gauge parameter, so there is y, which is vertical, and projectable. So it's a vector field which is projectable, and its ghost is -1. So it generates gauge symmetries of all of everything. But what we require that delta and small y is projection. So pi b of y is a projection which is small y. Start here somewhere. So then suppose that we have delta y of our section S 0. So suppose we looked for such a gauge transformation. Of course, we need to define gauge transformation for everything, but we require it to be projectable. So essentially, it means that we are actually interested in gauge transformations of these fields sitting here. And suppose that these are gauge transformation which preserve our background solution, then they are going to be symmetries of this equation. So what are symmetries? So for instance, if we have GPD, symmetries, not gauge symmetries, but normal symmetries, like global, physicists call them usually global symmetries. So symmetries, I need to remind what this. So V in X of E is a symmetry, a projectable in general, but often it's enough to consider vertical.
To B or to T?
No, just for GPD. In this case, if on E a projectable through this thing. But now I want to say what is symmetry of GPD. Not over background, just
of any degree.
Yes, in fact, it is in this. It is interesting not to restrict degree of V to be 0, because normal symmetries they have degree 0 in order to be able to act on sections.
So to say geometrical symmetry.
Yeah. Well, I would not call them geometrical, but they act normally on sections. Yeah. I hope to give an example with symmetries, not of this type, but it's start to be not very probable. So let's say if we have a section, then the delta V is of course just composition of sigma star V. So it's clear if V has non-vanishing degree, then it is just zero. It can't be not zero, so it doesn't act on section, but it acts somehow on gauge parameters in this higher structure sitting there. So for this to be non-trivial, of course, we need to require V to be of degree 0. And of course, there is an equivalence, like V is equivalent to V plus gauge symmetry, which is this guy. Oh, no, this must be vertical. Then I also need to act on sections. I also need to subtract projection. Yeah, minus, yes, minus V sigma star. Okay, then this
sigma is always of 0.
Yeah, when we speak about sections, we speak about maps, degree preserving maps. So the space of sections is not a graded manifold, it's a usual manifold. But if you want to get like again some structure of this type, if you want to, for instance, describe BV formulation of this, then you need to consider space of supersections. That's which is bigger, where you don't ask things to be degree preserving. Okay, so these are symmetries, and suppose I have a I have a symmetry here which preserves my particular background solution, and this defines for me a symmetry of my e to the of my e2 restricted to s. So my q with this y, let's say we define v to be like this, and this symmetry is no longer a gauge symmetry because my y does not preserve this in general does not preserve the structure, so it's going to be a symmetry of the GPD in a concrete background S. And one can do it other way around. If there is a symmetry in this language, you can gauge it. If you have, let's say V, it's really economical. Let me assume everything vertically. Really, of course, loss of generality, but not great. It's
Vertical with respect to which projection?
oh no. Now I start. Sorry. Now I want to start with certain, let's say, E prime, Q prime, T1x, just a gauge PDE. V is symmetry. And I want, with this data, I want to cook up gauge PDE over background. And this procedure can be called, again, it's a very vague term, gauging global symmetry. This is related to what we had in the example when the U1 symmetry of a Dirac field was gauged to and coupled to the Maxwell field. So suppose V is a symmetry. Then what we can do, we can introduce auxiliary variable C of degree 1. It's like a ghost associated to this symmetry, and cook a new E Q T1x, which is now a bundle over this one. I don't know how to, let's say, R shifted by 1 times T1x. So I add, I think of this coordinate C as a coordinate on, of course, everything is globally trivial, so it's not a big deal, as a coordinate here. So I extend my base.
Your symmetry defines the background, yes?
Yeah, I introduce new coordinate. I introduce it to background.
But
So my B in this case, B is R. Yeah, it's better to write like this. My B now is R shifted by 1. This is where C is coordinates times T1x.
so C is just a variable.
Yeah, one additional coordinate. I extend trivially. I just take a direct product of T1x with one-dimensional odd space where C is a coordinate, and this is my new B, and I declare it to be my new base. I pull back my initial GPD to this new base because it's clearly
Who is the homological field here?
yeah, and Q is Q prime plus CV.
Plus CV.
Yes. So, of course, this Q projects to C, and on B I have my gamma is just dx in this case because there is nothing left.
So Q is on E.
Q is on E, yes.
And CV is on B.
CV is also on E because C is.
But we need a field on B.
Yeah, but C is going to be a field.
It's a field.
So Q is in because I have a direct product. Yes. I just can sum up.
Yes.
So I take Q prime plus CV. I just take it, and then V is vertical.
This is a
new
field on E.
On E.
Yes, on B.
On B I have just dx.
So with trivial action on.
Yes.
Okay.
Yes. But of course, its coefficient here depends on this coordinate. In fact, even maybe let's.
What's R1?
It's real numbers, one-dimensional real space with shifted degrees. So there's a space where C is the only coordinate. One-dimensional. Well, constant. I don't know what in which sense. There is one coordinate. So the algebra of functions here is a two-dimensional space with unit and C, and C squares to 0. So, of course, all this is just algebraic objects, but geometrical intuition sometimes is useful. But so R1, by definition, is just a Grassmann algebra generated by one element. That's it. And this is this C. So I write this new Q. It projects to dx clearly because this thing is
just a little bit backwards. So V is a symmetry of E
prime.
Of E prime.
Yes.
And it is of degree 0.
Yeah, let's say degree 0 in this case. Yes, normal one.
So CV is of degree 1.
Yes, everything is perfect. In fact, a good idea, maybe to decorate it a little bit, once we understood it, as we discussed already. Suppose that there are few symmetries with index alpha, which form Lie algebra. Then I add here minus half, then it becomes a little bit more fancy, minus half CC in the sense of this Lie algebra d of dc. And then here I get this one because it is already Lie of B. So this is because this term was missing because I had only one symmetry, it commutes with itself. But if I have an action of Lie algebra, then a natural object is, of course, to write down Chevalier-Lindbergh differential, and this was the example which we discussed. But now the differential on B becomes not just dx, but dx plus Chevalier-Berg for this. And now it is, of course, becoming G1. Yes. Now it becomes less trivial. Okay, so this is a typical example. It's because V is symmetry, it commutes with Q prime. So this thing squares to 0. And because V form Lie algebra together with this P, this also everything is nilpotent. So we get a GPD over background, which is kind of gauging of the initial symmetry. But what is now my B? So let's look at B more carefully. So here is B. It's another GPD where gamma is dx minus half the CC d over dc, and I omit indices. It's clear what it means. So this is precisely the one which we studied, which is describing zero curvature equation. Solutions of this one are precisely flat connections of these values in this Lie algebra. So what happens here if we fix a non-trivial solution here, for instance, S star of C alpha is certain A alpha, which is now one form, and dA plus half AA is 0. So what happened? We coupled our system here to a flat gauge field, flat because it must satisfy zero curvature equation. So it's not very interesting. It's not very interesting situation, because indeed this coupling it only couples to flat connections. But in fact, it's not a big deal, because in this formalism, you can easily start to, by slightly changing the setup, you can start to consider curved connections. Or at least you could try to do it, because if you remember, I gave at some stage, and Dimorodinsky gave a talk, right, about this weak gauge PDEs. So we can actually equip this with an additional structure, with a distribution. So there is a distribution K, which is gamma invariant. And such that gamma squared belongs to this distribution. So we can try to deform the situation a little bit. We could.
So K is distribution on B.
On B, yes.
On B.
Yes.
Graded.
Yes, in general, of course. Yes.
Gamma is just a vector field.
Yeah. Now gamma is not necessarily homological, because this is
because of this.
Yeah, I can relax. So what you can do? You can relax the nilpotency condition.
Yes, we discussed it.
Yes. In this, for instance, in this situation, to generalize, you could do the following thing. You can take K to be generated by, for instance, something like this. Theta nu d over d c alpha. So consider these vector fields.
Theta are variables from
dx
somehow.
Yes. So what, and it's vertical, K is vertical. So what is it going to tell us? You see the structure of this vector field, the tensor structure of this vector field is precisely like the curvature. Because curvature of A is going to be two form, which means two guys like this, two dx's, plus one index of the Lie algebra. So what is it going to tell us? So what are solutions in this case? Solutions in this case, the definition of solution is slightly changed because now we only require that dx, in this case we call it s star minus s star q plus k is 0. So S is a solution if there exists k small in the distribution such that if you adjust q by certain vector field distribution, k, this is k, yes. Yeah, this means that because if you forget about this dx s star minus s star q is a vector field along section, along s star. So what I'm trying to say is that if this vector field along section belongs to the distribution pulled back to the section, then it is a solution. So it's you make it weak. What does it mean here? Let's take k to be theta nu, k alpha, few of them, f alpha mu of x d over dc. It perfectly belongs to the distribution. I just multiply this with generic coefficients. And if now I consider what this equation means, it simply is going to tell me that dA plus half AA is f, where f is, is this curvature. So by taking a suitable distribution, I can relax my zero curvature equation. And of course, there can be a contradiction. It doesn't mean that any symmetry I can couple to curved background, but I can study which case are allowed in order for this thing to be still nilpotent and all compatibilities to be satisfied. And then, for instance, a simple case like Dirac field and U1 symmetry, or multiplet of Dirac or scalar field with usual like UN symmetry or something like this, nothing happens. You can add on the base this additional distribution, and you will see that nothing is spoiled. You still get a consistent system, and it's going to describe for you the coupling of your initial system to gauge fields which are associated to your Lie algebra symmetry. And this you can call like gauging symmetries. So where gauge fields come from? They come from these ghosts. When you introduce ghosts for this Lie algebra, when you introduce coordinates on G1, they become coordinates on B by prescription. But because they are of degree 1, they become one-form fields. So this is what naturally happens. But in fact, if you suddenly found a symmetry which is of degree not 0, but for instance of degree -1, then you are going to do exactly the same, nothing changes. The only thing that your C is going to be of degree 2 in order for Q to be of degree 1 again, because this is -1, this is 2, and your gauge field in B is going to be a two-form field. So this is going to describe coupling of your higher symmetries to higher forms, and this is kind of subject which people are interested in the context of generalized symmetries. What about time? How am I doing?
Oh, I think you have, well, 20 minutes, something like this.
Okay.
15, 20.
Okay, then I think I'll limit myself to one simple example, one simple
Yes,
sort.
an example of such a construction, yes.
Okay, so one thing is linearization, which produces objects like background linearization. So if I start with GPDE EQ T1x, what I can do, this is what you call in, it's a GPD analog of what you call tangent bundle for equations. So what you could do, you could take vertical tangent bundle of E, VE in TE, and this is, let's say, PE, the projection. So I take tangent bundle, but in fact, I only take in tangent bundle vectors which are vertical. So this is canonical object vertical, vertical bundle. So then there is a natural Q. I take Q to be, first of all, there is a canonical lift of a vector field to the tangent bundle, but then we will observe that it preserves the vertical subbundle. So it's, let's say, Q twiddle on PE star F is, of course, just P star EQF. And because it's enough to teach this guy to act on linear functions, we just say that Q twiddle acting on P star DF, because DF is a linear function on tangent bundle. This we take, there is some fancy minus, don't ask me why. D, this by definition is D pi star of QF. So it's essentially, I'm saying Lie derivative. There are some subtleties. So this Q twiddle acts, if you identify functions on tangent bundle with tensor fields, then of course Q act by Lie derivative, and this is a natural lift. Of course, Q twiddle projects to pi star here of Q twiddle is Q. So it's a Q bundle, and so we can cook this. So now E is background, and now VE is like total.
Is the ground is linearization, yes?
Yes. So it's in UGPD for the moment. But it is naturally. So I just take VE. It's a bundle over T1x with an UQ structure. It's in UGPD. But because there is an intermediate projection PE from VE where it is from VE to E, then it has a structure of background PDE, where the initial PDE is a background. So what does it mean? If we pick a solution of our background equation, the resulting equation is just a linearization of initial. I think it's almost identical to what you have in the case of usual PDEs. The only thing that everything is graded. The language is slightly different. Okay, then where things become slightly more interesting and less trivial is when we study Lagrangian systems. And in Lagrangian systems, what we do, we have the following notion, what I call presymplectic GPD, which is not GPD in general, but otherwise names are very long. And this is the situation that you have EQ over T1x dx, but now we don't require Q to be a homological vector field. Plus you have a presymplectic structure, which is sitting in two forms on E of certain degree related to the space-time dimension, because of omega is n-1, where n is dimension of x. And there are compatibility conditions. Compatibility conditions are like this. Of course, d omega is 0. Then it is EQ omega plus dl belongs to certain ideal. So it's up to something, it's a Hamiltonian vector field. And there is the less trivial piece of the story, which is presymplectic master equation, which looks like this. It's half IQ omega.
So what is I capital?
I'll tell immediately, 0. So, so these are all axioms. So there is a Hamiltonian, which means that omega is invariant modulo this, and there is this equation which is generalized something, generalized master equation. So what is I? I is an ideal generated by one forms of the form pi star alpha. So I pull back my forms from the base, from T1x, and then generate the ideal. So roughly speaking, it is generated by dx and d theta in standard coordinates. So everything which comes from base, non-zero forms from base, generate me this ideal. So effectively, somewhere inside, it means that omega is, I don't have time to give another definition. What we are really interested in is vertical forms, because the quotient by these ideals are precisely vertical forms, as equivalence classes.
This approach, they are just horizontal forms. The one that...
yeah, but I don't have horizontal because I don't have connection.
Yes, but you leave
I take it as a quotient, yeah. I identify vertical forms as a quotient of all forms, modulo those pulled back from the base. So that's why this is like this, but this equation is exact. And this seems to be really interesting equation because this is maybe an interesting point of the story, that it stays intact, it survives generalization to this background story.
And omega degree and
yes. So once you have this data, you immediately have an action which on sections of this bundle, which is just integral of sigma star of presymplectic potential evaluated on dx as a vector field plus sigma star of L. This is kind of generalized Hamiltonian action. It's clearly first order. So this data defines it for you. But what is much less trivial is that if you extend it from sections to supersections, just replacing sigma with supersection, you are going to get something which is BV action satisfying master equation on the quotient space of supersections by the kernel of this symplectic structure. So it turns out that these axioms encode Batalyon-Vilkavisky formulation of a gauge theory. The only thing you need to assume that this omega induces the regular symplectic structure on the jet bundle of this E. Actually, vertical is enough, vertical jet bundle. But I don't get into BV story. So this gives me a nice way geometrical structure which generates for me Lagrangian gauge theories. And what is interesting is that its generalization to background is straightforward. So this presymplectic GPD over background is exactly the same story. So it's E B T1x. The only difference, all these objects are defined on E. The only difference that E gets replaced by EB. So now this equality holds modular forms on the total space E, holds modular forms pulled back from the base B, not from T1x. And then there is a statement that if S solution to B because I don't require any symplectic structure to sit on B, on the background. If S is a solution to B, then E restricted to S is a presymp GPDE. What is interesting is that this equation becomes it still stays. So it's kind of correct equation in this world when you define the structures on a bundle. These axioms, not only over space-time, but generic. So there is some right structure behind, which is not completely understood, but it just works. And that's what happens. So, and here is a promised example. So the example is gauging of higher symmetries of Maxwell theory. Very simple, stupid, but maybe it's easy to understand. So what? Let's illustrate how it works for four-dimensional Maxwell. So let's just do presymplectic formulation of Maxwell. So 4D Maxwell. We start with E, which is, let me just write coordinates. So I have space-time, this is my base. Then I have one coordinate of degree 1, and I have F mu, one coordinate of degree 0, which is going to be field strength at the end of the day. My Q is like this, so Qx is theta, of course, and Qc is something like half theta theta f, where indices are contracted. That's it, and then there is a symplectic structure omega, which must have, let me write potential, it's even more useful, which sigma, theta nu, f rho sigma dc. So this is symplectic potential, and omega is d of chi. Then this action is it's not a big deal to compute Hamiltonian. So you check that Q preserves this symplectic structure in the sense above. So you find Hamiltonian and you find what this action is. In this case, this action is precisely so this action is, now it depends on A and F, is d for x, f mu nu d mu a nu minus d mu a mu, plus or minus, anyway, I don't control this, like half f squared. The usual first order action of Maxwell, but what is less trivial that in fact if you go to supersections you are going to get BV for this story. Okay, so this no background, but in Maxwell there is an interesting symmetry of degree -1, which is just d over dc. Clearly, this thing commutes with Q and preserves symplectic structure, so it's a symmetry. So degree of this symmetry is minus of V is -1. Okay, so what we can do, we can actually gauge it just like we did for the example of just GPD, not presymplectic. So we add this C. So we add new coordinate B with ghost of B equal to, and we modify our Q to be new Q, let's say Q twiddle, equal to Q plus BD over DC. And then we compute the respective Hamiltonian. So let me. It's maybe easier if I look at formulas. I don't remember everything. So what we find that what the current looks like. So I v omega is going to be d f mu nu f mu nu theta rho theta sigma epsilon mu nu rho sigma. So this is a conserved current associated, which has a wrong degree, which is associated to this symmetry. It's just a Hamiltonian for the symmetry vector field. But now, because it's quadratic in theta, it has degree 2. And this is precisely the so-called surface charge, which is associated to symmetry of lower degree symmetries. Because if you integrate this object over, for instance, over sphere, because it's in our space, if it is 4-dimensional space, so in our space there is a sphere S2, you integrate, it's a 2 form. If you integrate it over here, you get electric charge inside, right? This is a standard charge. It's the simplest example of what's called surface charge, but in this game, the surface charge is a usual Noether charge associated to this kind of symmetry. Of course, it's known under a different name because this is global reducibility parameter. You can think of this V as a gauge parameter, which produces, because it's constant, it produces trivial gauge symmetry. And it is known, there is a version of Noether theorem saying that if you have global reducibility parameters in gauge theory, they are one-to-one with surface charges. So we just see the same, how the same objects are implemented in this game. And what we could do then, we could, of course, repeat this presymplectic construction, and we end up with an action which couple our system to this B field. And the resulting action reads like this. It's d4x. Here we have f mu nu, the same, d mu a mu minus d mu a mu, but now we get here b mu nu. This is B field, because B field has degree 2, so it's going to be 2 form. We find it here, and we get here minus half f squared, the same term. So this
is G. Is it G in front of B?
2. No, let's forget about it anyway. Coefficient is not important. So what we found, it's a known action which describes coupling of this higher form symmetries to the action, and so you get this B. If the topology of maybe I need to mention what it has to do with so-called generalized symmetries, or higher generalized symmetries. So what is clear that if our symmetries is a module over h of dx. So if on the base we have the RAM complex, if we have cohomology,
H of dx is not an algebra.
No, it's the usual in forms, the exterior algebra.
No, what you wrote homologies of.
Cohomology. It's
they do not form an algebra.
They do under exterior products.
If you multiply
2 cocycles, I get cocycle.
no, but if you multiply it by a function, you
No. Symmetries is a module over other way around, sorry. Symmetries is a modulo of the RAM cohomology. So if I have a symmetry, suppose I have this guy, this V, which is D over dc. And suppose I have one form, alpha, from H1 of dx. So not trivial cocycle, one form, which is closed but not exact. Then I form U1, I multiply this guy, I get V prime, which is alpha d over dc. It is still a symmetry because it commutes with Q, because Q contains the RAM, so it doesn't see this guy. But what happens, because this thing has degree 1, this thing has degree 0. So it acts on sections. How does it act? It's clear. Delta V prime acting on my field A, which sits here, is going to be just alpha. So it's what I do, I add cocycle to my one form. And it's not a gauge symmetry, because gauge symmetry is when I add exact form. This is gauge symmetry. But if cohomology is non-trivial, then I have a possibility to shift these lower degree symmetries. I can uplift them to degree 0, and they start to act on sections in a non-trivial way. And this is, of course, a well-known symmetry, which is called one-form symmetry in this context, which only makes sense if on the base you have non-trivial DRAM classes. Yeah, I think it's already late, and I already took a lot of your time. Unfortunately, there is one thing I really wanted to explain, but it's impossible. Maybe privately at some stage I wanted to show one thing. But at least I hope it gave a spirit of what you could do, that you can play this game of coupling systems to certain gauge fields. And an interesting story, which is not really explored, is that you could try by changing this background PDE by adding non-trivial distribution. You can try to curve the background geometry. So what you could do, for instance, the only example we can see that you can see the conformal scalar, just conformal in the sense of usual 15-dimensional conformal algebra, just Poincare plus special conformal transformations and dilations. So you gauge it in a certain way. So you end up with something which is perfectly defined, but on a conformally flat space, which is where the flat connection is just a Cartan connection of this conformal geometry. But for scalar, of course, we know things are simple. It is compatible with introducing non-trivial distribution in the background GPDE, which describes curving this geometry, and you get a correct coupling to the scalar curvature. But this is, of course, far from being a very general situation. But the hope is that it should have certain link, for instance, to problems that people consider in the context of conformal geometry.
Okay.
Thank you.
Thank you very much.
Delay.
Questions, remarks? Okay. Thanks again. So this is our last session in this semester, and we hopefully meet in September. Goodbye.
Thank you.